Hey, and welcome to another episode of Debugging Maths. In this video, we'll be discussing the most important types of matrices, very common, and the probability of you being tested on these types of matrices is extremely high. So, let's talk about them. So let's talk about the identity matrix. So the identity matrix, also called the unit matrix. Unit meaning one, right? The identity matrix. So the identity matrix is a fancy way of writing one in matrix. So the number one, right? The real number one. If you want to write that in matrix, you'll be referring to the identity or the unit matrix. So it's a matrix that. So basically, if you see this matrix, you are referring to one like this. This is the unit matrix. It's another way of writing one. So you have 1, 1, like all the leading diagonals. So this is called the leading diagonal. This 1 and 1 here, leading diagonal, and the 0, 0 is second diagonal. I'll talk about that as we progress. But this is a 2 by 2 matrix now. This is matrix A. This is a 2 by 2. So in a 2 by 2 matrix, this is how you call 1. So, and of course, if it were a 3 by 3 matrix now, you can see 1, 1, 1, and then every other part is 0. So once you see a matrix like this, you are referring to the identity, right? That's what it's called, the unit identity or 1. So let's move on. So let's also talk about transpose of the matrix. It's not a type, but let's just add it to this one. So the transpose of a matrix is basically us interchanging the rows and columns. So when you interchange the row and column, you are doing what is called the transpose. It can be represented using this letter like this. You see A transpose, or you can have it like this. It's like saying A transpose, A complement, A do something else. That's what this superscript transpose is saying. A do something else. You get, like transpose, or in set you can see the complement. So A complement or A transpose. So let me explain briefly what this means. So the transpose or the complement of a matrix refers to interchanging the row and the column. So it means make row column or turn row into column. So now this is the first row now, 2 and 1. Let's turn this first row into column. So that is 2 and 1 becomes column. So 2 and 1. And when we have the last one, 2 and 2, let's turn that into a column, 2 and 2. So what is the transpose of A? Or you can have this to transpose. So the transpose, like we said before, is just us interchanging the row and turning it into column. Step by step, let's turn this first row into column. That's 2, 3, 1. This first one, let's turn it into column. 2, 3, 1. Very simple. Now the second one, turn it into column. You can see the pattern is very simple. 1, 4, and 2. And the last one, you turn the last row into column. Very simple and systemic. So 9 like this. Now you have succeeded in transposing matrix A like this. This is transpose. Very simple. Let's go on to the second type of matrix. So the diagonal matrix, as the name suggests, is truly diagonal. So when I say diagonal, I'm referring to adjacent, right? So I'm referring to this here, diagonal, like this, like a cross. So anytime you hear diagonal, just remember the word cross, and that is the way the matrix look like. The matrix looks like a diagonal, or rather, the matrix mimics the pattern of a diagonal. So what the diagonal matrix is basically, by definition, so the diagonal matrix is a type of matrix that has in its principal diagonal real elements, right? Non-zero elements. When I mean non-zero elements, I'm referring to 1, 2, 3, 4, 5 numbers that you can count, and their negatives, -1. In matrix 2, we add their negatives to it. You can see this one here, -3. So when you have in the principal diagonal, when I mean the principal diagonal, you know we have two types of diagonal. So this first one here is called the principal or the leading diagonal, or the main diagonal, if you call it that, the main. Why this second one here, this 0, -3 and 0, is the second diagonal? Makes sense, right? So don't forget that too. So when you have in this first diagonal here, it's very, very simple concept. Non-zero elements, non-zero entities. So as you can see, you can find real numbers here again, just like in C, just like in A. You can find real numbers 1, 2, and 3. You can also have negatives if you like. And there's another very important thing. You can see that the main, all the elements that are not in this main diagonal, they are all 0. That's how you know it's a diagonal matrix. And another very important thing, please listen to this. They are not equal. 1 is different from 2. 2 is different from 3. 2, just like in A, is different from -3, and -3 is different from 4. They are not equal. So the moment you have another element here, let me give you another example. So the moment you have another element here, -3, -3, this is not a diagonal matrix anymore. It has to be different elements, 2 different real numbers, 2, maybe 4, and they are all different in the main diagonal, and then 0, 0 elements in the non-main diagonal. So like this one now, this -3 disqualifies it. Or in another case, look at this one. We have 1, 2, and we have 0 entering inside the main diagonal. It disqualifies. This is no longer a diagonal matrix because there's 0 here, and here something is repeating itself in the main diagonal. So this is no longer a diagonal matrix. So these are very good examples of diagonal matrix. You can see 2 and 3 and 0, 0 elements that are not in the main diagonal. So this is very correct, and this one too, you can see, very correct. So in the scalar matrix, remember what I said in the diagonal matrix? Remember I said something very important, that in the diagonal matrix, we don't have anything repeating itself, and therefore it's a diagonal matrix. Now the scalar matrix is a type of diagonal matrix with the principal or main diagonals having equal elements, like 4, 4, 4, or whatever. So of course we'll have 0 elements in the non-main diagonal region, or all the elements that are in the main diagonal are all 0 elements, like this. See, 4, 4, 4. That's why it's a type of diagonal matrix, but this time we're not having equal elements. So the moment you have, let's say, 2 and 2, and then you have 0 and 0, so this is a 2 by 2 now. You can see this is a scalar matrix. We have 2 and 2 in the main diagonal, and of course non-zero elements. So the triangular matrix is another very important matrix. So you need to listen carefully about this matrix. No, you will get it confused, but it's very, very simple. It's all a pattern. So you can see it's like this kind of triangle, like this. So there are 2 types of it, by the way, but let's just get the concept down first. So it's a matrix that you will find that has real elements above the principal diagonal. The principal diagonal itself and the elements above the real, you find real numbers above. Remember what we said about real numbers, like 1, 2, 3, and their negatives, -1, -2 in matrix. That's what we refer to as real numbers. So you find those numbers in the principal diagonal, the main diagonal above, and 0 elements below, like this. So you find 0 here, 0 here, and 0 here. So the zeros are carrying a triangle of real numbers, why the zeros are the base in this case. So like I said, we have 2 types of triangular matrix, very easy. So in this matrix, we can either have the triangle, the real numbers will form some type of triangle, upper or lower, like this. You can see real numbers there forming this kind of triangle here too. This is where the triangle stops. This is the base of the triangle. So you can see real numbers forming this triangular pattern here, while below the main diagonal you can find 0, 0 elements. So the 0 elements below are carrying the triangular real number. So that's why it's called upper, like this. So you can see the triangular pattern while you find 0 elements above the main diagonal. So 0, 0, and 0, like this. So this is in a 2 by 2, and then this is 0 here. you can also have them here. See, so real numbers forming the triangle, and you can have the 0 here. So don't forget this. It can also happen in a 2 by 2. In this matrix, you find elements weirdly looking the same in the northwest and the southeast direction. Look carefully. You will find, anytime you find elements like this, see 3, 3, can you see the pattern? You can find elements weirdly looking, they are exactly the same in the north, this diagonal here and here and here. So they are the same. So whenever I find that kind of pattern, then you're dealing with a symmetric matrix. So for me, the way I detect that the matrix is symmetric really fast is to find the transpose. Remember what I said about transpose? So now let us find the transpose of this matrix. Like I said, to find the transpose of this matrix, you need to turn the row into column, interchange them, turn the row into column. Now, if you find a matrix having the same transpose, like whenever I transpose the matrix and it is equal to the same matrix, then you are dealing with a symmetric matrix. So that's another way of finding out. Like you can see now that this is symmetric. Look at 3 and 3, 6 and 6. You can find elements in the northwest and the southeast direction, northwest and southeast direction, having the same elements, the same numbers. And of course, when I transpose it, I still get the same thing. So one other very important thing that you should know is that the trace of the matrix should be equal to the transpose of the matrix. So what do I mean? Remember what I said about transpose. Let's transpose A. So A transpose will be equal to, of course, let's turn the row into column. So turn this first row into column. So that's 1, 2, 6, 1, 2, 6. Turn it into row, into column. Second row into column. That's 2, 3, 3. And lastly, 6, 3, 9. So now what is the trace of A? So the trace of this A will be, of course, let's add the main diagonals together, 1, 2, and 3. Let's add them together, 1, 3, 9. Let's add them together. That's 1 plus 1 plus 3 plus 9. So this here will be 13, right? And the trace of the transpose, which is this matrix now. So the trace here of this matrix now should be the same. So that's 1 plus 3 plus 9. See, it's still the same thing, which is 13. So that's one fun fact you should know. The trace of the matrix, original matrix, when transposed, the trace should still be the same. If it's not the same, then something is obviously wrong. And of course, finally, we have the idempotent matrix. So the idempotent matrix is another very interesting matrix. Very simple. It says that when you have a symmetric matrix, so what I mean is, let's assume this now. So let's say we have this symmetric matrix. So anytime a symmetric matrix is multiplied by itself, it reproduces itself. Like this. Whenever you multiply this matrix by itself, it will reproduce itself. This is a symmetric matrix. How? It has 0, 0 repeating itself here. And like I said, if you want to be sure that it's a symmetric matrix, transpose the matrix. If you transpose this matrix and you still get the same thing, then you know that it is symmetric. So remember what I said about transposing matrix, turn the row into column. So that's how I know this matrix is symmetric. So this first row becomes 1, 0, and this second row becomes the next. This second row becomes the next column. So 0, 1. Now I know this matrix is symmetrical. So now we know that the transpose of this matrix is still the same matrix. Now we know this matrix is symmetric. So every time a symmetric matrix multiplies itself and that matrix reproduces itself again, they are referring to an idempotent matrix. So don't forget that. Alright guys, so that's it for this video. Make sure to use the comment section if you learned anything new. And thanks for showing an interest in maths. Keep practicing and I'll see you guys in the next one.